Now for the second part, we're now going to just proceed to show that 3-set is NP-complete, and we'll do it by reducing from circuit set. Okay, so this was a two-part proof outline that I mentioned before. We finished showing that circuit set is NP-complete. We're now trying to show that 3-set is NP-complete, and we'll reduce from circuit set. Okay, so 3-set is NP-complete. There's the theorem. This is the Cook Levin theorem officially. I reminded you what the definition of 3-set is. It is those formulas that are in 3C and F, that means and of ors formula, which there exists a satisfying truth assignment. And we talked about a little bit the connection with this, between this sort of Boolean logic kind of question and something that seems a little bit more like a combinatorial puzzle, which helps explain why it's important. All right, so we're going to show that it's NP-complete. We got to do two things. We have to show that this language is in NP, and then carry out the reduction. And a claim that we already essentially showed that it's in NP, right? We said that this, when we talked about circuit set, right? If this, we can express this language as those formulas phi, such that there exists an assignment where that assignment, where you can check given phi and the assignment whether that's a satisfying truth assignment in polynomial time. Okay, so same argument as we had for circuit set. All right, and then for the interesting part, we need to show that 3-set is NP hard, and we're going to give a reduction from circuit set to 3-set. Now, let's pause for a moment before we actually start to do this and think about what does this mean. So we have a circuit, a Boolean circuit. That's our instance of circuit set. And it's either satisfiable or it's not satisfiable. Either there's some assignment to it, it's variables that makes it output 1, or there's no such assignment. And we want to produce an instance of 3-set, so we need to produce a 3C and F formula which has the same feature that, either it, if this was satisfiable, then this thing should be satisfiable, meaning that there's an assignment to the variables that makes it output 1. Or if this circuit set instance was not satisfiable, then there should be no way to set the variables here so that it outputs 1. Okay, so one of the things that's tempting is to observe, well, okay, circuit set is a big instances of big Boolean circuit, and here I'm supposed to produce a circuit of a certain type. It's supposed to be just like a big and of ors. So maybe I can just sort of kind of come up with an equivalent circuit that computes the same function as the circuit that was the instance of circuit set. And that would be a perfectly good reduction if you could do it. So the thing to just keep in mind, you have to maybe play around with it a little bit, is that it's very easy to come up with circuits where if you try to make them have this and of or format, the smallest and of or format will be exponentially large in the size of the circuit. Okay, so you can't carry out the reduction by just taking the circuit that you have and trying to massage it into the format of a 3C and F formula. Okay, maybe some of you already could see that, but that's not going to work because in general that will take, that'll blow things up by an exponential. Okay, so we have to do something that's a little more clever. And remember, a reduction just gives us a lot of freedom. So we just have to produce some instance of 3-set, a collection of clauses that are simultaneously satisfiable if and only if the circuit is satisfiable. And to do that, we're going to do the following trick. So let's sort of set the stage. So we're given a circuit, instance of circuit set. It has variables x1 through xn, and it has a bunch of gates. They are AND gates, OR gates, or NOT gates. And let's give names to those gates. Let's call them G1 through Gm. Okay. So our reduction, which I'll call f of c, is going to produce a bunch of clauses that together are going to form the formula phi. And those are going to be clauses which involve variables x1 through xn, just like the circuit had, and g1 through gn. So we're going to treat each of the gates as having an associated variable, g1 through gn. Okay, and now remember, a clause is one of these, in the earlier slide, it's a parenthesized expression with the or of 3 literals. variables or the negation. And a perspective that's useful here is that a three-set instance, so a 3CNF formula, is satisfiable if and only if all the clauses are simultaneously satisfiable, meaning there's some truth assignment to the variables that makes every one of the clauses simultaneously true. And because they're connected by an and, that's exactly what you need to make the whole formula true. Okay, so the way we're going to proceed is we're going to produce a bunch of clauses that enforce that these gate variables G, I'll call them gate variables, take on the values that they should take on, that they would take on if the circuit was functioning the way a circuit functions. And I'll say what I mean by that in just a minute. Okay, and we're going to throw together a bunch of different clauses, one for each gate, so that all together, if you satisfy all those clauses simultaneously, you basically must be setting these gate variables in the way that they are set as the circuit functions, and that will give us the sort of hook that we need to carry out the reduction. Okay, so here, so I guess I sort of said how the reduction works. For each gate, I'm going to produce a couple or three clauses that I have to sort of throw into the bag, and then the collection of all those clauses at the end is going to be our instance of 3-set. So let's start with a negation gate. So let me tell you what I mean by this picture. So the gate is G sub I, it's a negation, so it has one input. And now that input might come from another gate, or it might be one of the variables x1 through xn. I'm just calling it z in this slide. It could be either of the two things. And whatever it is, we produce from this gate the following pair of clauses. And so gi or z, and not z or not gi. And the thing to notice about this pair of clauses is that that is logically equivalent to this Boolean expression here, that z is true if and only if the negation of gi is true. Okay, in other words, z and the negation of gi have the same value, or z and gi have opposite truth values, which is exactly what should happen when you have a negation gate, right? The gi gate value is the negation of z. And actually, if you don't want to sort of carry out the manipulation yourself, you can just look at these two clauses and see that the only way to satisfy both of these clauses is if gi and zi have opposite values, right? Because if both of them were true, for example, then this clause would not be true. And if both of them were false, then this clause would not be true. But if you have one true and one false, then you can satisfy both clauses simultaneously. Okay? So this pair of clauses enforces the assertion that gi has the opposite truth value as of z. Okay, so what should we, so that's for negation gate. Now let's take care of the other two kinds of gates. So we have I guess an OR gate next on this slide. So an OR gate, it's one of the gates in the circuit. It has a gate variable G sub I associated with it. It has two inputs. Let's call them Z1 and Z2. Again, the inputs might come from other gate variables. It might be other gate variables, or they might be other inputs, X's. For this OR gate, we will produce these three clauses that are listed here. And those three clauses enforce the following, they're logically equivalent to this thing in red, which asserts that gi has the same truth value as z1 or z2, which is exactly what gi is supposed to do. Gi is an OR gate. Okay, and so you have to sort of carry out a little manipulation, multiply things out, and then simplify them so that you get it as a collection of ORs. But indeed, this works. And you can also just look at these three clauses and check for yourself that I don't know, if Z1 and Z2 are, let's say, both false, then gi is supposed to be false, right? And so if the Z1 and Z2 are both false, and you somehow set gi to be true, then you would not satisfy these clauses, right? In fact, you would not satisfy this last clause. Okay, so you can go through and try it out carefully, and you'll see that exactly the ways in which these clauses are satisfied are the ones in which gi takes on the value of Z1 or Z2. Okay. So we've taken care of the nots, the ands, the ors now, and then we have to do the ands, and not much changed here, but so between the two slides. And now we're doing and. So we have to look carefully. There's the GI is now an AND gate. It has two inputs just like before, Z1 and Z2. And then here are the three clauses that we're going to sort of throw into the collection of clauses that we're building up. And they are logically equivalent to this assertion that Z1 and Z2 is equivalent to GI, which is just what we want. Okay, so you go through, in your reduction, you go through each gate in the circuit and you throw in the collection of 2 or 3 clauses that are, we've just specified, and throw them all together. Okay, and those clauses collectively all constrain these G variables to take on the values that they actually take on if you plug in a certain input, Boolean input to the circuit. And then the last little thing we need to do for our reduction is that we need to assert in our reduction that the 3-set instance, the circuit outputs 1. And so our reduction will add one clause, it's just a singleton clause, G sub m, where G sub m is the output gate. And that's a clause that can be satisfied if and only if the output gate outputs 1. That's the intention. Okay, and that's our full reduction from circuit set to 3-set. So you go through gate by gate, throw in the 2 or 3 clauses to your collection, and then this one final clause for the output gate. Okay, so let's check to see if this in fact did what it was supposed to do. So is this computable in polynomial time? This time I think it's pretty easy, right? It's a simple transformation. You just have a collection of 2 or 3 things that you need to add to your collection and just write them out one by one as you go through the different gates of the circuit. So it runs in time proportional to the number of gates of the circuit, which is the size of the input. Does yes map to yes? So if I have a yes instance of circuit set, did I produce a yes instance of 3-set? Let's check. So if it was a yes instance of circuit set, that means that there is some setting to the x variables that causes the circuit to output 1, which is a satisfying assignment. And then I claim, well, if you just go through and assign those x values to the x variables, the ones for a satisfying assignment of the formula that we've built up, and the gate values of C when evaluating x to the G variables of the formula that we built up, then that gives a satisfying assignment, right? Because every gate variable in our formula phi you will assign it the value that the circuit assigns it as it evaluates the value x, and all of those clauses will then be satisfied, including the final clause, because the output of the circuit on this input is 1. So that all told, that's a satisfying assignment because you simultaneously satisfy all the clauses. So that's yes maps to yes, and then no maps to no. We have to argue that if the circuit was not satisfiable, then the formula that we built up, the 3-set formula, is not satisfiable. And we'll do that by proving the contrapositive, as we often do in NP completeness reductions. We'll show that if the formula that we built up is satisfiable, then that had to imply that the circuit we started with was satisfiable. So let's do it step by step. So if we have a satisfying assignment to our formula phi, it assigns values to the x variables, to the g variables. And what do we know about that? We know, well, let's work our way down. We know that the output gate variable g sub m must be assigned 1 because we had that singleton clause at the very end, right? And every other gate has to be assigned the value it would take given the values of its inputs, because that's what our clauses forced, right? That was the only way you could satisfy those collections of clauses, one for each gate. And you have to satisfy assignment if we're talking about phi being satisfiable, so there's some assignment that satisfies all of these clauses simultaneously. Well, then if you work your way all the way down to the x variables at the input level of the circuit, the assignment to the x variables must therefore be a satisfying assignment for C, because they must be consistent with the x variables and the g variables all must be consistent with the evaluation of the circuit C gate by gate. And it must have been that circuit evaluation in its final output gate assigned to 1. Therefore, that assignment to the x variables had to have been a satisfying assignment to the circuit C. And so that shows the other direction of the reduction, the other half of the argument, that if the circuit was unsatisfiable, then phi had to be unsatisfiable, and we proved that by proving the equivalent contrapositive, that if phi was satisfiable, then that implies the circuit is satisfiable. And that's the whole reduction. So that was in 2 steps, the Cook Levin reduction that shows that 3 set is NP complete. We did it by first getting a generic reduction from an arbitrary language in NP to the problem, to the circuit set language. We did that by building a circuit that mimicked the functioning of the Turing machine that decides that verifies that NP language, A, given a witness and a input. And then once we had a circuit set in our hand, instance of circuit set in our hands, we could reduce to 3 set, and we did that, as we've just described, going through the circuit gate by gate and adding a collection of 2 or 3 clauses, which all together, if they were all satisfiable simultaneously, had to force the assignment to the X variables, as we just noted here, to be a satisfying assignment to the circuit. Therefore, the circuit had to be satisfiable. Okay, that's all. Thanks everyone for listening.